Welcome to this video. So in this video, we are going to design the Watchdog timer on the onboard computer. So essentially, the Watchdog timer is a piece of circuitry that is used to basically monitor the operation of the microcontroller or the chip or the IC. So what it does, it tests or keeps checking whether the MCU or the IC is stuck in an infinite loop. And then if it's stuck in an infinite loop, based on the timeout that you have set, it resets the chip or the IC. Basically, this is called kicking the dog. That's why it's called a watchdog timer. So most ICs have inbuilt watchdog timers, which are okay, simple to use and implement. I mean, you only require a software layer to do that. But for critical systems like this nanosat, you require rather I require an external watchdog timer that is separate from the IC that it is watching over. So what I'll do, I will add a circuitry for the watchdog timer, and then we'll use that now to connect it to the MCU itself. And normally, the structure or the architecture that is used to design a watchdog timer is such that you have, let me just illustrate, you have your MCU right here. So this is the MCU, right? But then you have just a minute, MCU. But then you have watchdog IC here. So this is a WDT watchdog timer. Watchdog timer at this point. So WDT circuit, right? And then WDT circuit. Now next you have connection to the MCU. Now what's recommended is that if you have a power supply that's supplying 3.3 volts to your MCU from maybe another IC here that is maybe giving it 5 volts. Let's say it's giving 5 volts, stepping down to 3v3 positive. Someone might decide to share this way, which is okay if this watchdog IC requires 3.3 volts. But to make the system more robust, I prefer to have a separate MCU for the watchdog timer itself. So this is also 3v3 volts, right? So this is the architecture we are going to use. Design this circuit, look for an IC for watchdog timer, and then connect it to the MCU. So to cut the research or to not waste a lot of time, I have looked into an example of a watchdog timer IC. I'll just open LCSC here. LC. Look for an IC called the Max 6814. So 6814 is actually very few are in stock. But we can use it still. Let's see about that. By the time we manufacture these boards, I hope that this part will be in stock. So you can use this. place it right here on the schematic. Place. And place it here. So the next thing that we do as usual is to open the datasheet and check what type of connections we need for that IC. So basically, you see this is a microprocessor. It's trying to it's protecting oops, microprocessor. Then the max this is active low, watchdog out, a masked interrupt, I think, ground, watchdog in to this. Yeah, so this is the architecture. Let's look at something else. Power supply, maximum is 5, so you can supply it 3.3 volts. These other things we'll look at them during the firmware development. Another thing is a pinout. So watchdog output, active low, pulses low for 140 milliseconds. Okay, ground no connection. Watchdog input. All right, supply volt, that's fine. Okay, so it says that if the microprocessor does not toggle the watchdog input within TWD 1.6 seconds, then it asserts this line. So it writes the watchdog output line. All right, then let's see when basically I'm filtering out information that will enable me to draw the circuit. The software part, we'll look at it later. The watchdog timer is serviced within the watchdog timeout period. Software considerations. Okay. That's it. So it's easy as that. So let's translate this into software. So what we need is just VCC, these two lines. So you can see this is an unmasked interrupt or unmaskable interrupt, if I'm not wrong. My processor, yeah, an unmaskable interrupt. So the reason why I highlighted it is because to reset an MCU, there's what we call a hard reset and a soft reset. So soft reset is done mostly through interrupts. Hard reset is done through maybe giving it a new power cycle, turning it on and off, or pressing the yeah, actually the power cycle. That's a hard reset. So what I'll do, I'll connect this pin to the reset pin of the MCU. So right here, the first thing is you place a not connect flag. And then VCC should be 3.3, but what I want to do is connect, this will be WTT 3V3, right? Then ground is here, ground is right here. Okay, so this is active low. So watchdog input should come from the MCU. So I'll just add a net here and call it WDI, and then this other guy right here is WDO out. So WDO, it's active low, so you can use, I think, is that, yeah, to put a bar on top of it. Then these two are connected to the MCU. So if you look again at the data sheet, this WDO is going to the unmaskable interrupt pin. So basically it's going to the reset pin, this pin right here, reset. Okay, so what I'll do, I'll connect this line using a 0 ohm resistor to this line right here, just to be safe in case I want to disable that line. So let me check whether I have a 0 ohm resistor. 0R, find 0R. Let's see this one. Yeah, I have a 0 ohm resistor. So when you're designing, I could have used another part, but when you're designing, you want to minimize the number of parts that are different. For example, I don't want to use a 0 ohm resistor and still there is another 0 ohm resistor in the schematic. So I want to keep the components as common, or rather as same as possible. So this pin right here, let me put this. I can put this to this side, and then this should be WDO. Right there. Okay. So the next thing is this pin. I think this is used to set the timeouts and whatnot to PB15. Let me put it on PB15. PB15 right there. Paste that, and that should be the Watchdog timer. I see. And the last thing is the supply voltage. So supply voltage, I need a 3.3 volt regulator. So I'll copy this one. Actually, I'll copy this whole circuit. I'll copy this whole circuit and paste it right about there. So to keep things modular, I can paste it here, close to the part it is supplying. So you notice this part, actually I just noticed that it doesn't have an input voltage. It's supposed to receive 5 volts, and similar to this, supposed to receive 5 volts. And now this net should be WDT 3V3. WDT 3V3, then it comes to this pin right here. Yeah. Or even to make it more readable, I can connect it that way. Okay. So that's the Watchdog timer IC circuit. Watchdog external, Watchdog, external Watchdog. Right. So the next thing we want to do with this schematic, I think now it's a high time we route it, and if we make any changes down the line, we'll be updating. Okay, so what I'll do, I didn't actually look at the cost of this, just remembered that. Let's see, I always look at the price of these ICs. 1 unit is going for $3. That's expensive. $3, okay. Right. So let's convert this to PCB. So save it and then go to the PCB here. And we had already done some dimensioning. So what you'll do, you come to design, you import changes from schematic. And you apply changes. So it tells you import is finished, and you should be able to see all the changes that you have made, you have added. So this IC is, did I select it? This IC is, where is it? It's right here. Okay, cool. So let's lay out the OBC part. So these are the nanosat dimensions. I'll keep repeating this. The one U 90 millimeters by 96 millimeters PCB. So the other thing we have to do is now place this ISA connector somewhere up here. So I'll just open a diagram that will help us to place this. So on my GitHub, or the GitHub for this project has a diagram that shows how it's placed. Yeah, you can see this now. This is I'll open it in a new tab. So if you look closely, you'll see these pins at this point. This is 2 by 32 times 1 connector. Then this, the second one, is 2 by 20, 2 rows by 20 columns connector. So this is the one I'm using, the 2 rows by 20 columns. Is it? Yes. So this is 1, 2. Yeah, these are 20. So we'll just arrange it to follow those standards. So I'll take this and paste it right here. So screw 1 should be, I'll follow the IC naming conventions, which goes counterclockwise. So I'll place it right about there. Then screw 2 should be here too, right about there. Screw 3 should be on the edge. Screw 3 should be here. So let me zoom out a little bit to make sure they align. Okay. Then this other guy should come to the top here. So what I'll actually do to make sure that I am following, I mean, they are the same dimensions, I'll move this a little bit and measure from this point to the center of where I want to place it. That's 5 millimeters. 5 millimeters. Let's see. 5 millimeters around that point. All right. So if I draw a line from this point, wait, layer. Let me go to the mechanical layer. Draw a line from this point to that point. So if you notice, this is not at the center, so I'll move it a little bit to the center of that, right about there. Okay. Then the other one is from this point to this one. Those are straight. And then to this other guy down here. So this looks like it's a little bit off, but it is still within the tolerance. And then these other right there and finish. So if I move this and just clean this a little bit. Oops. Clear. Okay. Let me just move it right there. Yep. Right there. Then move this screw also a little. Move this one a little. That's okay. Nope. this, just checking. Okay, so what I'll do is I'll place this at the center right there, and then place these at the center also right there. Now the other two, if you look at the diagram, you can see they are offset a little bit further than these others. Yeah, so what we can do about that, we can actually, let's look at an image of CubeSat, 1U nanosat PCB. People have done these things, so I want to confirm that everyone follows. Actually, it's a standard practice. You should follow the standards that have been set, unless you really have a reason to tweak it. So if you look at this, for example, this PCB, you can see these two. Sorry, open in new tab. You can see these two are right next to the connector. These others are on the edge. All right, let's follow that. So I'll place the connector. Connector is right here. I'll place it on the bottom side. Bottom side on right there. And then I'll place this connector next to it. Next to it like that. This other one also. I think that's cool. Then I can delete these construction lines. Okay, save that. Now let's go to our MCU. So what I like to do, I like to split this window into two, and I want to open a new window. Then push this to the side, minimize this part. So as it's opening, I can place this MCU at the center, just at the center right there. Then we have these other parts. So let this schematic open first. So I'm going to do just the layout, and the routing we'll do it in another video, so that we keep the video short. So the schematic is right here, combined. Okay. So the reason why I do this is to cross probe or cross check which component is selected. So if I click here, I should be able to select the MCU. Yeah. If I click this one, should show me the MCU, or I press Shift X. If I press Shift X, yeah, it can should show that. All right, so the first thing is for the MCU. Where's my laptop lagging? It's slowing down. So I'll just copy. I'll highlight all these capacitors. They should be highlighted here. There they are. Drag them to the PCB board, and then just arrange them. These capacitors should be close to the MCU that they are decoupling. So I'll just arrange them that way, like that. How many are they? 1, 2, 3, 4, 5, 6. So there are some others over here. 6. So drag these two just about there. Then copy that. Highlight, rotate, and place them close to the MCU, right about there. Okay, the next thing I'm gonna do is the voltage regulator for the MCU, which is right here. So it's highlighted. I'll highlight this part that way. Should be highlighted here. Yeah, here it is. Drag it. So this pin, these are toggle pin from the EPS board, and ideally you want to place this on the edges, on the edge. So I'll place it right about there on the edge. I'll place the MCU, the voltage regulator LDO, next or close to the MCU, and then the capacitors also close to the MCU. These are the capacitor. I think it's, yes, this one. So place it right there. So 5 volts, 5 is right here. So when you're placing components, you just want to make sure that you make you try to make these route tracks as short as possible. As short as possible. Yeah, so 3v3 can be here or can be right here. Then these 5 volts can stay there. All right, save. There's enough space to go around anyway, so space should not be a worry at this point. And the other accessories are this part for programming. For example, let's put up the boot toggle. The boot toggle is here. So drag it. So let's watch that. Rotate a little bit. So boot 0 pin. Yeah, that is okay. That is okay. Then spooled high. Let me copy this 1, 2. Not this. So this is the reset button, I think. Yeah. So the reset button can stay. Reset pin is here, so you can put it down here. And then these pins, this resistor and this capacitor, highlighted. Here they are. Sometimes the scope is too huge, so you have to bring them close to each other. Okay, so move that to somewhere around here. So reset, can place it there. Then this also I can place it right there. Okay, so this pin is Watchdog. I see. I have this capacitor. I think I've not placed it yet. A VCAP capacitor, so I'll drag it all the way here. Rotate a little bit and place it right there. Then that is placed, this is placed. I think that section is done. The next thing is the debug header for programming. So press on it and you can see it highlighted here. Move it to somewhere around here. But what I want to do is place it somewhere that it will not interfere with these other pins. So the best place is to have it here on the edge, close to the edge. Anyway, I want it on the edge for this PCB. Or for aesthetics, it can actually stay. No, let it stay right there. Because when you're inserting this pin, this header, you don't want to be close to this. This is another header also, so you don't want to be close because of the usability of the PCB. So the other thing is these two LEDs and its resistor. So here they are. I'll just place them in a series line. Move it to somewhere around. Where is that pin connected at? This LED is not connected, so to the MCU. So what I can do is connect it first. Is it connected really? Or is it user LED green? This should be a net label. Paste that, enter, and save, and then refresh it on this other side. So go to view, design, design, or is it? Oops. Design import changes. Update net. Okay, so it's connected on this side, so I'll move it to that side. Right about here. But to make it look better, I can rotate this that way and put this next to it like that. Okay, save. The other thing is the user button and its capacitor. Actually, the user button does not have a pull-up resistor. That's strange. It should have a pull-up resistor at this point, 10K pull-up resistor. So I'll copy this and put it here. Pull it to 3.3 volts. So again, save, and then come back here and update the net. What changes? Yes. Okay, so if we select this, should be able to see it right about here. So I'll bring it closer. So this button, this is a resistor, so place it close to the button, and then the capacitor, also place it close to the user button right there. then maybe pull a little bit to the left, to the right, and then copy it, and it's connected to this side, so put it right about there. So I'll place this here. Okay, that's that. Crystal. So crystal and its capacitors. Pull it a little bit, arrange the capacitors. So I want to do that. Arrange it that way. And this other one, arrange it that way. So this crystal capacitor should be kept as close as you can to the crystal itself to filter out the noise actually. So this is a 16 megahertz, so it might get a lot of noise very fast. And then we place it next to the MCU. Let's put it right here. Okay, we have another crystal, I think. Do we really have another crystal? No, we only have 16 megahertz. Yeah, so if I select all these parts, they should select here. Oh, there's one part remaining. So what is this? This is the reset resistor, pull-up resistor. So it's right about here. So I'll place it right there. Save. Okay. Next thing is we lay out the USB-C debug. I mean, we have laid out this, have we? The watchdog timer, have we laid out that part? No, we have not. So let's put it. Watchdog timer, arrange that part. So if you notice that I'm arranging these parts in terms of blocks, so components that belong to the same part or IC are placed close to each other. Okay, so that one can stay right there. There's no problem, but I can rotate it a little bit or place it right about there because of this pin. Okay, good. The next thing is let's lay out the brown note detector circuit. Brown note detector is right here. So this circuit again is used to detect brownouts in terms of the power received from the power received from the electronic power supply. So you notice that we used a watchdog timer IC, but there are some ICs that are called supervisory ICs that combine watchdog timers with brownout detectors and power monitoring. But they are complex to use, and I don't want to waste a lot of time designing something that can be done in two separate parts. It's not really worth the trade-off. But yeah, if you want to do that, you can also do it. Yeah, use a supervisory IC that is combined combined. This is USB-C, so let me place it on the right, and then this moves a little bit. USB-C. USB-C. Place it right there. The resistors. These resistors are for, one is for V bus, the other one is for, this is for CC1 and CC2. One is a capacitor. So I'll rotate this and pull it a little bit to this part. Rotate it. Let's see, rotate it again actually. Just looking for the best way to place it. This is like solving a maze. Yeah, that works. So rotate this that way. Place it there. Rotate this way. Place it on top of this, like that. Okay, then we have, after that capacitor, we have this R7. Where is R7? R7 is right here. So we place it here. Place it right there. These are differential. There's some differential pairs, so I'll give this a little space. Then you have an ESD diode. Where is it? It's down here. So USB signals require, it's not a must, but to make it more robust, you need to have these ESD diodes. So I'll place it right there. So I'm leaving this space to be able to route the differential signals from this point to the USB. Okay, so what's the other thing? So this USB-C is okay. Then if you notice that this board is too huge, or rather not too huge, it's a standard size, but the components are few. So because I intend this design to be an educational kit, like for nanosats, I will put a lot of labeling, around the components themselves to label this specific parts. But I might also reconsider that. So the space is actually a blessing in disguise if you think about it that way. All right. So save this.